Okay, so dilations, that means that you're making something larger or smaller, like when you get your pupils dilated, when you go to the optometrist, they're making them open up. They're the same shape they were before, they're just getting larger. Um, in mathematical terms, it could be getting smaller as well. It just depends on your scale. So if we look at these, um, the pre-image is dashed and the image is solid. So the properties, well, so a dilation is the basically the stretching or shrinking of an object centered around some point generally. So it's the stretching or shrinking of an object. And when I say stretching, I don't mean stretching like you stretch rubber band. I mean just enlarging altogether. So the question of if it's an isometry, well, unless I can pick up this little triangle and move it and make it big, and not just because of the way your vision works, but like actually make them the same size, then it's not an isometry. It's, if you look at the pictures, it's making them bigger, it's making them smaller, and in fact that's kind of the definition of a dilation. So it is not an isometry. It changes their size, and really that's its whole goal. So no, and it's, different sizes, not equal measures. The properties of dilations are, you notice none of these kind of got rotated or anything. So the corresponding segments are all parallel. This one's parallel to this one. This one's parallel to this one. That's parallel to that. That's parallel to that, and that to that, and so forth. So all of the corresponding segments, and that means the segments you started with and the ones you ended up with from them, are parallel. The corresponding angles are the same. So this angle is the same as this angle. This one's the same as this one. That one's the same as that, and that as that, and so forth. So they are congruent. And then corresponding sides are proportional. So this one compares with this one the same way this one does with this one. So like these two triangles are similar because of that proportion. Okay, so this would have been proportional. Okay, I've recopied these figures so that we can refer back to them. Using figure C, so there's C, A in the pre-image, which remember was dashed, is negative 1, 2, 3, 4, positive 4. And B was 4, negative 4. And C was negative 4, negative 4. In the solid one, A is negative 2, 2. B is positive 2, negative 2. And C is negative 2, negative 2. Now, what happened from each of these? What is the pattern? Basically, every value, every component stayed exactly the same but got halved. Negative 4 went to negative 2 in all cases, positive 4 went to positive 2 in all cases, so everything got halved. So then if I just tell you outright the scale factor for C is 1/2, then what does scale factor mean? Well, scale factor means the thing that you multiply all the lengths by to get the new object. So you might not just multiply all the numbers. The reason this worked out is because the dilation is actually centered at the origin. on the graph. So it's centered here, and so that's why you can just have all the numbers. If it's not centered there, then you can't. But whatever the situation, wherever it's centered, the lengths of everything will be multiplied by the scale factor. So the length from B to C, for example, used to be 8, so now it should be 4. The scale factor for figure A, so if you look at figure A, we've got 0, 2, 0, 6. This one appears to be centered at the origin. You can't really normally take that for granted, but let's go 2 directions or 3 and see what happens. So we went from 0, 2 to 0, 6, and we went from -2, -1 to -6, -3. And this one went from 1, -2 to 2, -3. So we appear to be multiplying everything by 3. So 3. And figure B, so we start with the dotted one. And we go from, let's find one that's on an intersection somewhere, 2, -2 to 2, -2. That one goes down here, so it's 4, -4. So this appears to also have a scale factor of 2. So the other one was a half because it was getting smaller. This one is 2 because it's getting bigger. And this is really the only one that's on a dot. But we could kind of try to decide the distance from here to here. You go over 1, 2, 3, 4, 5, 6, 7, and down 2. And from here to here, you kind of go 3.5 and down 1. So in both cases, 3.5. So 3.5 times 2. So this is 2. So in C, it was 1/2 because it got smaller by half, and this one doubled. So the relationship is similar, but if you have a scale factor bigger than 1, then you're getting bigger, and if your scale factor is less than 1, then you're going to get smaller. So if we want to list examples of dilations in the real world, I'll put this on your quiz, and it will not be able to be auto-graded because who knows what you can come up with, but you might have as an example, if you make a photocopy and you change it from 100%, then if you do bigger than 100%, it gets bigger. If you do smaller than 100%, it gets smaller, but it stays proportionally all the same. So that's an example of a dilation. If you have a model of something, a scale model of a car or a house, if you're an architect, those kind of things. Those are examples. Okay, so ABC, we want to go from the origin, which is good, because that means we just have to multiply numbers. And we want to have a scale factor of 2. So because it's from the origin, I get to multiply all the points by 2. So B is 2, -1, so it's 4, -2. A is -1, 1, so it's -2, 2. C is -2, -2, so it's -4, -4. Everything gets multiplied by 2. So there's my new one. On this one, we want to do by a factor of 1/2, which means we half everything. We multiply everything by a half. So C was -1, 2, 3, 4, 5, +2. So we need -2.5, +1. A is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 2.5, 2.5. And B is 1, 2, 3, 4, -2, so 2, -1. So again, all we're doing is taking C for example, was -5, 2, and we go to C prime, which is then a half times -5, 1/2 times 2, so C prime is -5/2, 1, and that's where I plotted that there. This one is slightly different because we're not centered at the origin. So what we need to do is multiply all the distances from the point around which we're centering, which is 2, 2, right there. We need to multiply all the distances. So we're multiplying the distance of 2. So to get to A, not from the origin like we were doing before, but from here, I would have to go -3 and -1. So I'm going to go -6, -2. And there's A prime. To get to B, I would have had to go down 3, so I have to go down 6, B prime. And to get to C, I would have had to go over 4 and down 4, so now I have to go over 8. Oops, I'm off my graph, and down 8. So there's C prime. So it still got larger by a factor of 2, but this time it moved. And the reason it moved is because everything's basically expanding away from the center point, and since the center point was not in the triangle, it scooted away. This one, we're still going to center around 2, 2, but now 2, 2 is inside it. So it'll stretch around it or shrink around it instead of moving away or towards. This one we want a scale factor of 1/2. So to get to A, I'd have to go over 2 and up 3. So instead I'm going to go over 1 and up 1.5. And there's A prime. To get to B, I would have to go over 2 and down 4. So I'm going to go over 1 and down 2. And to get to C, I would have had to go over 6.5. No, I mean 7, sorry. 1, 2, 3, 4, 5, 6, 7. So I'm going to go 3.5. C prime. So again, if your center's in it, it'll stay in it. And if it's not, then you'll move away or toward it. Okay, so in the film, Honey, I Blew Up the Kids, he causes the 2-year-old boy to be 112 feet tall. If we assume that the average height of a 2-year-old boy, obviously I mean 2-year-old there, 2-year-old boy is 3 feet, then what was the scale factor of his enlargement? So we took 3 and we multiplied by whatever that factor was, and we got 112. So there's really feet, but these cancel because they're identical. So 3K is 112. So we would divide by 3. And really, that's as good an answer as any because this doesn't exactly come out, but so I'm perfectly happy there. If you really want to, you could say 37 1/3. This is a somewhat better answer because this almost looks like you're multiplying, but whichever one you're more comfortable with, I'll understand what you mean. If we have an equilateral triangle with 4-inch sides, and we undergo a dilation with a scale factor of 2.5, the question is what happens to the side lengths? Well, basically, in a dilation, everything about it, not the angles or the, anything like that, but all of the measures get multiplied by the scale factor. So the area, would get multiplied by the scale factor squared because it's in both directions, but any length just gets multiplied by the scale factor. So it would be 4 inches times the scale factor, and we would get 10 inches. Okay, so that concludes transformations, and I will set about getting all of these linked and creating assessments for all of them, and hopefully have that finished in the next couple of days. And then we'll start on the next group.